Alright, so I have started. So, what I was saying is that last time, if you remember that 4-bar linkish question, they have the vector loop like this. I'm going to elaborate a bit more on the reasoning behind these minus and plus signs. You know, the sign of each of the vectors. And so as you can see right here, it's R2, R3, R4, R1, right? Does that make sense? So that was how they went through the first time, which if you look up here, it is R2 plus R3 minus R4 minus R1, which is what they have right here. So what I was going to tell you was that after they solve the equation like that, right, they get their, their x's and y's, their scalar equations, which are, remember, these right here. And then they further break it down right here by getting rid of the cosine of the angle 1 because it's 0, right? Anyway, you guys remember this question. So then on the next one, if you recall, I talked about this very briefly. On the next one, they have a different direction for vectors. They have R2 plus R3 plus R4 plus R1. So essentially it is the exact same question, except that the vectors have changed. And so, well, the vector directions have changed. So essentially they're all positive, right? So if they're all positive, what you have gotten, very simply, is the exact same equations, just with different signs, right? And so they are essentially the same equation. And that is written here in the text somewhere. I'll find that exact passage so you guys can read that. So it says the above equation is essentially the same as equation 5, which was the first version, right? The signs of R4 cosine theta 4 and R4 sine theta 4 are the opposite of those in equation 5 due to the changed definition of theta 4. Theta 4 in equation 8 is greater than theta 4 in 5 by an amount of pi, which reverses the sign for cosine and sine functions. Thus, if we use theta 4 definition of figure 3, then it becomes, let me see, then if we use theta 4 definition of figure 3, which is this one. Alright, where did I end up? Then the equations become identical to equations 5. So it says equation 8 contains 3 variables. So essentially what it is saying is that you get the exact same thing by just changing the equation by the sign, right? So what it is saying is simply that the sign doesn't matter. It's arbitrary. And so more or less we're focused on that. We're focused on essentially you just getting these equations, right? So this passage, if it makes more sense to you to read it yourself, I encourage you to do so. But let me see this one. Yeah, I mean it. So basically what I'm expecting of you guys is nothing has changed except that I'm just expecting you guys to end up with something like this, right? I want you to have this equations, like the actual equation, variables, everything right on that end, but the sign is something that is arbitrary. So, because as you can see, right, this exact same question, they added all of them and then they subtracted 2 of them and they get the same thing, just using a definition of a previous angle. So it doesn't affect anything. Don't worry about it if it does. If you get something different, it's okay. Like I said, this right here, this passage from this book is chapter 2, which is online. Start from 19 and go through like 21 or something, and you should get to that, and you can find it and see if it makes more sense to yourself there. Alright, so that was the first thing I wanted to touch on. So the next thing is that we are going to do some other examples. We have to do rolling contact. That's right, rolling contact. I forgot. So rolling contact. Let me see where it starts at. Yeah, rolling contact. So, right here. So it says rolling contact, so it's position analysis and mechanism containing a rolling contact pair. So rolling contact equations for two rollers. So it says rolling contact exists between two element surfaces when there is no relative sliding at the contact point. So the length of the element that passes through the point of contact must be equal for the two elements. This principle is used to relate arc distance of the element of one link with that of another link to establish the equations governing the rolling contact pair. So essentially what it is saying is that as both of the rollers come into contact with each other, or two surfaces come into contact with each other, one is rolling, the amount of distance on the circle, right, as we roll, so like let's say it looks something like this, and it's in contact with this surface right here. As this surface rolls, right, let's say it's rolling this way, you know, as this surface rolls, essentially it's going to go forward, right? And as it rolls, the distance that it makes on the arc length, right, as it rolls, is going to be the exact same distance like down here, essentially, right? So basically what it's doing is that it's relating arc length and the radius of this circle to the arc length and radius of another circle, or the change in angle to another circle, or the ground, and how much distance you moved. All right. So this'll, like I said, that was what that first passage sort of meant, but we're gonna give you some good examples here in a second. So it says, consider the mechanism in figure 11 consisting of three links. The ground link is holding the two rollers in contact. So that is probably this one right here. Right? So it's this right here. So essentially as this rolls, this red part, this highlighted part, is the arc length essentially of this circle. And as it turns, you guys would probably agree that this distance right here, basically their contact distance has to be the same, right? Would you agree with that? Because if they're contacting at one point and they continue rolling, they both have to be, if they're both in contact that whole entire time, then that means that they have to be the same, right? Would you agree with that? Okay. So basically, this is a case that we don't see very often, and I don't know if you guys, you know, so do you guys remember like Calculus 2 or something, where there were like specific cases for like equations where you had to use like L'Hopital's rule and stuff like that? For this right here, there are cases, but you don't have to like do anything special with them. The equation just changes, and so you just have to remember what the equation is and how you relate these two surfaces. So we're gonna go back up really fast. And so it says, the ground link is holding the two rollers in contact. Each roller has a revolute joint with the ground at its center. Assuming the lower roller to be the driving link, the input, the motion of the driving and driven links can be related. Number the ground as 1, driving roller as 2, and driven as 3. Next, imagine that link 2 is painted on one side. As it is rotated, part of the paint transfers to the roller as shown. The arc shown to the left of the joining line of the centers of the two rollers must be equal, since we assume rolling contact exists between the two rollers. Thus, the arc length shown as the red left of the center line on link 3 must be equal to the arc length shown to the left of the center line on link 2. Recall that arc length is equal to the product of the radius of curvature and the corresponding central angle. Let rho 2 and rho 3 denote the radii of rollers 2 and 3 respectively. So, we have this. So this is your very first rolling contact equation, right here. Your very first one, this is the basic one that all others kind of spring from. So just to expand this a little further, rho 2 is the radius of curvature. So essentially the radius of the roller 2, right? I think we can all agree on, I think we all got that, hopefully. And then inside the middle is delta theta 2, and delta theta 2 can be expanded as what it'd be, or not delta, whatever, it's, I suck. So it's theta 2 minus like theta 2 naught, and it's equal to the same thing on the other side. And what that means is essentially, I'll get to, whenever I get to it all written out. So what this means is essentially that rho 2, the radius of curvature of roller 2, times the change in angle 2 has to be equal to rho 3 times the change of angle 3. That is what we've written out here. And so delta theta 2 and delta theta 3 are these quantities right here. It is just simply the change of the angle of 3 and 2. So if you see delta theta 4, it is the change of angle of delta 4, or theta 4. Right? Does that make sense? Give me a 100 in the chat. So essentially this right here, so remember I told you that in some questions you will need an additional equation to solve your problem, right? Doing your vector loop. This is an additional equation. As you can see, it has theta 2's in it, right? Theta 3 in it. These two are known, rho 3 and rho 2, just simply because that they are radiuses of the circle that we can measure, right? And so, yes, it only works when it's a rolling contact. That is a good point. Thank you for bringing that up. So this only works in rolling contact. So do not try anything like this. If it's a roll slip, a slider, a revolute, anything. Like, you cannot do it unless it specifically states rolling contact. And generally speaking, it's fairly obvious when it's rolling contact because it'll look, well, you'll see it in a second, but it looks like what you'd imagine. Now, right here. So as you guys see right here, this is a positive relation, right? You see that these are absolute value, which means that it is a positive, right? It's always keeping the positive. As you can see here, we've now have a negative in front. And the reason why we have a negative in front is because we have external contact is the next type of rolling contact. And what that means is that essentially, let me roll this out. Where did they show that? Figure 11. So figure 11 is external contact. And so the actual equation for what that figure 11 should look like is this right here. And so I didn't want to confuse anyone, but this is essentially the base equation right here. This is what we start with. But for this one down here, that one we just looked at, it should be a negative. And the reason is because it is external contact. And so what external contact means is that essentially the rollers are touching each other, like basically one is not inside of the other one. I guess that's like a way to put it. They are externally contacting, but one is not inside of the other one. And you'll see, I'll show you an example of what internal contact looks like, and then you'll be able to see the difference. So this right here is external with the bad writing. External contact. Now, and external contact makes it to where you have to have a negative in front of the other one, or one of them, right? Now let's move into internal contact. Internal contact looks like this. So you see the difference? Essentially, this circle is rotating with respect to this one as well, right? So what I meant was essentially internal contact is literally internal. It is one roller is inside of another one. External is the opposite, where both rollers are not inside of each other. They are rolling on top of each other, but one is not inside the other. You see? So this right here, internal. Does that make sense? So, like I said, internal contact versus external contact, all it does is change the sign. That is all. It just changes the sign. So let's go back up here. So right here, external. And then if we have rho 2 delta theta 2 is internal. You see? So just I mean, since obviously the homework's online and the exams are online, I don't think you'll ever have a problem remembering this. But the point is that you should just know this off the bat, right? And there's some reasoning behind it, which I will talk about in just a second, but we do need to be fast. So it says, in external contact, the rotation of the driver and driven rollers are in opposite directions. That is the reason why there's a negative sign put in front of it, right? So like, for example, if you spin this one right here, right, essentially it's saying that they're in opposite directions. There you go. That's external contact. Internal contact, they are not. They are both rolling in the exact same direction, which means you don't have to have a negative sign. And now here, this is something I need to, this is the one that shows up more often, is this. So this is another case. So real quick, this right here is the basic equation. So this right here is basic equation, right? The next ones are the ones that come up more often. And this is this one right here. And it says, when the centers of rollers are not stationary, then the rotational arcs on each roller depends on the relative angular displacement of the roller with respect to the vector connecting the centers. Figure 12 illustrates the general case in which the center of the rollers translate as the driving roller or transmits rotational motion to the driven roller. Therefore, equation 24 must be modified so as to account for the relative displacement of each roller with respect to the vector connecting the centers. For external contact, it is shown. So, once again, external contact, how it looks right here, they're contacting externally, not internally. There is a negative sign, right? That's the first thing we notice. The second thing we notice is that this equation, the very first one we have, which I'm going to write up here, delta theta 2 rho 2 is equal to, I did it out of order, but that's okay. So essentially the next thing you notice is that inside of here, we no longer have just delta theta 2, right? Or delta theta 3. We have delta theta c, and that is that part that they talked about after, which was the relative angular displacement of the roller with respect to the vector connecting them. So right here, if you look at this picture, right? Look at this picture. You will see that this is the vector connecting them, right? So I think we can all see that. So the vector connecting them is this part. It is R sub A, right? R sub A. And so R sub A is the vector connecting both the centers of the two rollers. And as you can see here is essentially because these two are rolling with respect to each other, like they're actually moving. Like this center, as you can see from this picture to the other one, it has moved a little bit, right? It has actually came down here this way. That means that this vector, RA, is now further down, right? So basically what this equation keeps track of, it keeps track of that original delta theta 3, right? And delta theta 2, which is the change in angle here, right? But it also subtracts off the change in the vector A because their centers are moving with respect to each other. Does anybody have any questions about like why, like this right here, like how they got some of this? Essentially, think of this like a correction factor. This is like how I'm gonna portray it, which I mean it's not Does everybody know what a correction factor is? Essentially, what a correction factor is like it's something that you subtract or multiply on to like try and get. It's something that's used in like mostly like higher level math or like higher level like physics and science. Essentially, it's something that you multiply or add on that gets your answer back to. I guess it's something that's useful during like changing of units. So like think about it that way, right? So whenever you're changing from like Fahrenheit to Rankine or something, you add on something to get to Rankine. Think of it as like that. Essentially, what we're doing here is that this original equation at the very top is just changing. It's the radiuses times the change in angle, right? Over here, if you look at this one, is that this right here is the original one, right? The change in theta 2, right? And this right here is the original change in theta 2, right? This one versus this one, right? So what it's doing is that it's subtracting off the R part, or the change in delta theta A, to get you back to what it was before, like back to the original way of the equation. So you can see right here, this right here, it's showing you right here inside of this circle as the change of delta theta 3 minus delta theta A, right? And so basically it's like getting rid of excess parts to get you back to what it was in the original, what it worked as in the original. At least that's how I look at it. That could be, totally off base, but that's what it seems like to me. Essentially, it's just trying to get the equation. It's something we added on here to get the equation to make sense again, right? But for you guys, when it comes to solving problems, what you guys are going to do is, let me rewrite this. You guys are going to have to identify this type of question versus another type. So like if you saw a mechanism that looked like this, you would have to know that the equation is this, right? Does that make sense? And then the second one is row 2. A. Okay. I could not have driven a worse A. Alright, so. And now obviously this is plus or minus though, right? Like you guys understand that depending on how they contact, it's plus or minus, right? I'm going to put that right here. It's plus or minus this, right? So depending on how it's contacting, it's plus or minus. But it's internal versus external. Yeah, you understand? So those this right here so far are our ones that you'll see, right? These are it's the basic equation, the second like variation of it, right? And then right here it's the same thing, right? Remember this is plus or minus. So this right here this is the equation I wrote. It's this. I wrote A. It should be C, I guess. We'll go with C. That is my fault. I think there's an A in here somewhere. So, this right here. So this is like the second so this is the second variation for a rolling contact of two rollers that are rolling about each other, right? And now here, this is the third one. The third case is rolling contact for flat contact, or rolling on a flat surface. So this is one you'll see a lot. You will see this a lot. Because a lot of questions have like some roller rolling across something flat or angled, right? So this is something you'll see very often. So real quick, this right here is the first one. So this vector is r. They've defined this vector as r, right? That vector is r. And as this thing rotates around, right? As this thing rotates, essentially you are getting more of this area contacting the ground, right? So right here it hasn't contacted really yet. Then as it rolls and translates, now half of it has, and this pink is in contact with, it has rolled on the ground. And essentially, this length of right here that's on the ground is the same length as that, right? And so for this type of question, we are relating not the angle change of the ground, right? Because the ground's not changing angle. We're relating the angle change times the radius of 1, so the arc length of this circle, right? So we're relating the arc length of this circle with respect to how much distance we've gained on the ground, right? So as you can see here, is that as this thing rotates, and by the way, this makes sense if you like think about it for just a half second. As this thing rotates, the ball has moved forward, right? The circle has moved forward. And so what it is saying, our equation is representing is, depending on the angle change, right? How much angle, so basically how much angle change equals how much we went further, right? And so this equation is this. It is the change in distance, or the change in this vector length, right? So you notice how we started here? Our vector length has gotten this much longer, right? Oh wait, no, it moved back. Oh, okay, so they're showing that one first. Yeah, I think they're showing the other case first. So they're showing the one where it moves backwards first. So that's what I meant. So essentially, this is the sign change of this type of question. If the rotation is making this vector length smaller, which as you can see right here, it very clearly is, you have r as, that length, and then it got smaller because of the rotation is moving it this way, right? Therefore, the vector length got smaller, and since it got smaller, that means you have to have a negative s, or a negative sign. So essentially, for this top equation, it is delta r is equal to negative rho 2, I guess, times delta theta 2. So these ones are pretty simple, pretty straightforward. It's just the change of it's the change in the vector r, which could be, by the way, which could be r2, it could be whatever the number is, right, for the vector. But the change in vector r is equally related to the radius of the circle times the change of angle, right? Essentially, it is the length that we have changed is equal to the arc length, which makes sense, right? I mean, I don't. There's no other easier way to put it. Is that essentially the distance we traveled on the ball is the distance we traveled on the ground, right? So that is that equation, right? And now, on the bottom one, the bottom case is the exact same, only we are moving further, so R2 is getting bigger. So as you can see, R2 is right here, and we have moved this exact same rotation as before, but only because R gets bigger. As you can see, after stage 1, it is now longer. That means delta S is now a positive quantity, or delta R is now a positive quantity. So therefore, it is the exact same, except delta R is equal to rho 2 delta theta 2 with no sign change. There was not a negative put in front of this because our R got longer, right? We didn't lose distance because of how the ball was rotating. It wasn't coming back toward us. You know what I'm saying? So if you put the ball on the ground and rolled it forward, away from you, right? That is a positive change of R because it's moving further from you. Therefore, it'd be a positive answer like this. If you put the ball down in front of you and like spun it backwards, like you do with a basketball or something, and let's assume it stayed on the ground the whole time, for rolling contact's sake, that is a negative change, and therefore you would have to have this equation right here. So the sign of this one depends solely on the length of r. If r gets smaller, negative. If r gets bigger, positive. So it's probably the easiest way I can put it. So delta r is equal to rho 2 delta theta 2. That is the third case. Let me see this one. Okay, so this is the next one. Where's figure 14? That's figure 15. Alright, whatever. So it says, figure 15 illustrates how to determine the sign of a rolling contact equations for the general case in which both the flat and roller rotate. So relative rotation between the roller and the flat determines the angle corresponding to the arc of the roll. Figure 15a shows the choice of r for which the r increases for a positive relative rotation of the roller with respect to the flat. So right here in 15b, we see the opposite. So 15a is this one right here. So now things have gotten a little more complicated, right? So we start here, right? We start here. And the ball is rotating, similarly to the last ones, this way around, which means that it has moved further down. You see? And so r has now gotten bigger by this amount, right? Which is right here. It has gotten bigger by that. So, although they use S for this one, so I'm not sure why they use S for this one. I can't remember. Maybe it explains it, but maybe it was just to deviate between S or the like a flat surface and a one that was not, I guess. But so as you can see though, as this thing rotates, we have the exact same thing happening. This gets bigger, the arc length, obviously rolls against it. We have moved forward, right? So this right here is the same thing. So I'm going to use their definition. I'm going to use delta S. Just so if you guys see this in the book or something, it'll make sense. But delta S is equal to rho 2 times delta theta 2, which is nothing new, right? This is the exact same thing we had before. Only we had to add something else too. And we had to add this delta theta. And I believe, which I will make sure in a second, that delta theta is the angle change of this flat, or this like surface, which I will look in a second to be sure. Okay, it doesn't say. So it says relative rotation between the roller and the flat determines the angle corresponding to the arc of roll. Figure 15a. Okay, so they didn't really explain that one very well, did they? No, they did not. Okay, that's unfortunate. So, let me see if there's like a better way to put this. Somewhere in here. So row 2 is now all the way over here. Yeah, okay, so it is. It's it is that. It's the rotation, or it's the angle of this. So it's the change of this here to this. So as you can see, this flat piece that it's rolling on has become more or angled, right? It is that. I've had to look at the picture for a second, and it started to make a bit of sense. But just real quick though, this right here is not something that you will ever have to solve for, right? Like once again, the important part of this right here is theta 2 or some sort of r, right? Which because that's what we're trying to eliminate, right? if you wanted to find this angle change, you could do it. So essentially, it's not something we're looking for. We're looking for the things that are in our question as unknowns, and that's something that if something is an unknown, but we can go out and measure it or find it, right? We don't really care about it. We're looking for things that you cannot measure at all times, right? So let me put the fourth case over here. And so the whole point of this, right, is just to give you another equation that represents the rolling on the ground. That's all the reason for this is, right? So this is in case, and by the way, you will have questions, maybe one on your exam, wink wink, that has a rolling contact on it. So you will need to know which of these equations to use. Now, once again, I realize that since the exam is online, like I was born at night, but not last night, I know, right? Like I'm not dumb. But the thing is that I need you to understand why we select it, right? Not just go on here and go, oh, well, this looks about right. I want you to know why we select it and, how to apply it. Does that make sense? Can I get a thumbs up in the chat, if possible? There's been like one message today. You guys are all asleep. And here comes Jackson with something. Hopefully. Not asleep yet. Thank you for leaving me room to improve to get you to sleep. Anyway. So this right here, these are all the rolling contacts. And like I said, all of this is online. The book, the notes, if this doesn't make sense, go and look it up. I promise, if you read this and you put some thought into it for a second, you will figure it out. I promise you. It is not, we're not sending, Voyager to Mars or something, right? This is something, it is not that bad. If you look at it for a little bit, you can figure it out, I promise. So everyone understands, hopefully, where all of these come from and how they are applied. So just to recap really quickly, I'm going to go back up to the first one. This is the general case. So it is rho 2, it's the arc length of one has to be equal to the arc length of the other, right? Fairly straightforward. And then over here, we have an external contact where the arc length of one has to be related to the other, right? But it's the negative arc length. Essentially, since they're moving in opposite directions, that's how it works, you see? So you have to put that negative sign there, which is this right here. And then we have the next case right here. So we've taken care of this one. The next case is this, which is, very simply, whenever we have this center and this center moving with relation to each other. So like, for example, let's say this was like geared, right? Like let's say these were geared together, which I don't know. Actually, no, let's not say they're geared together. Let's say that, for example, the driving gear, which I believe is, I would say it's this one. I don't know though. I don't know which one they said is driving. But anyway, whatever it is. Essentially, these two are connected through the middle, right? They have some sort of link, like the ones we've been seeing in this class, right? There's a link connected in the middle, holding them in rolling contact at all times. And there's some sort of driving mechanism, like an electric motor or something, whatever it is, right? And it is spinning this along the outside of this circle. However it's happening, it's spinning along the outside of the circle. And so our equation, which is this one right here, represents the arc length of one with respect to how much this middle thing is changing. So essentially it's the arc. So this right here is the normal arc length, right, of a circle. This put together is the normal arc length of, or this is the normal angle change of just rolling contact minus how much this is changing. Like this whole piece on the outside, basically the vector connecting them, the thing connecting them. It's that. So once again, I'm just trying to get you to understand where all these terms are coming from. They are coming from simply the normal angle change. This right here is the angle change of the vector connecting both of them, or the link connecting both of them. All right, moving down. This right here is probably the easiest one. I'd probably say is the easiest one. Delta R is equal to rho 2 delta theta 2. Essentially, it is the change in this length has to be equal to how much this arc length was, right? Or how much contact we have with the ground. So for this one right here, our length was this long. Let's say it was 10, right? Let's say this length was 10 feet, 10 miles, whatever you want it to be. 10. We lost 5 because this arc length was equal to 5, right? The contact with the ground was equal to 5 because we rolled back towards us. That means that our R is now 5 because we did 10 minus 5, we got 5, right? That is what we are, that is this. Essentially, the direction of the rotation got our vector to be smaller. Therefore, we have a negative number right here, a -1 attached to rho 2 rho 2 delta theta 2. So essentially, ball rolls whichever direction it rolls, the vector got smaller or bigger, and the arc length of the ball contacting the ground has to be exact same as what we put onto how the distance we traveled, right? All right, and then it's the exact same thing as the other one here, positive, switched up. Jackson's got something for me, hopefully. We shall see. Is it just variables or numbers that we solve? So that is a good question. So what he's saying is, in an actual question, is this equation, are all these equations actual numbers or are ones that we solve for? These are just variables until we know some sort of input. So like I said the other day, if you put this into an equation solver and you were one equation short, you would not be able to do it. But with the addition of this equation, you would, knowing some sort of input, right? And in this class, we don't really care much about the input. So this class used to. It used to before I taught it online, basically, because everyone had access to MATLAB. And so the professor before me, Dr. Farhang, he would give you a question that would tell you an input. Like he'd give you some sort of input torque or input like angular velocity, and you would be able to solve for it. You would actually be able to get an answer for all the variables. But the problem is that we don't have access to MATLAB anymore because you are probably sitting in your underwear at home. So we can't do that. So we're setting everything up. We're trying to set everything up so that you guys can solve for it, right? And that is basically what my hope is that if you guys can set this up, if you guys got on MATLAB or, even Excel or something, you guys could do this, right? If you could set this up perfectly and put all the equations into an equation solver, knowing some sort of input, like let's put it this way. If you wrote all the equations, let's say there were 3 equations and 3 unknowns, including this one, right? If you wrote 3 of them into an equation solver and then set, like, let's say theta 2 is equal to, theta 2 is equal to something, and I told you it was equal to 45 degrees, it would spit you out all the other variables, right? So basically, if you can get the equations by hand, you can do it on equation solver. It's just a matter of typing it in. It's not, there's nothing different about it. Now MATLAB has its own set of code, right? Like you have to actually type in MATLAB speak for it to work. But once again, that's just a function of you knowing the software. It's not a function of you knowing what you're doing, right? That's what I'm hoping for. I'm hoping for everyone in here to be able to get the equations to set it up, and then, do the question. I might actually do that. So my friend actually has a copy of MATLAB for Life, and so I might have him record him doing a question, and he'll just do it on the screen, and I will narrate it or something so you guys can see it, just to show you that this is not all just I didn't create this and just go, haha, how can I screw over my students today and waste their time. No, it actually does have some use and can be solved. So, I don't sit in my room and, stroke my cat and twist my mustache and think of evil ways to waste your time. So, I don't have a mustache, by the way. I can't grow a beard, really, but that's beside the point. So, we got this right here. Everyone can kind of see how that one works. And then the last one is very simply the one before it, only we are now, so basically, these two are very similar in that we now have to relate a change of, the change of the vector in between for this one. And this one is it's the exact same one as the previous one, except we are now relating the change in the surface, right? Like if we're on a seesaw, the angle has changed walking from one side to another, even though I rolled a ball across. That's a good way to put it. If you rolled a bowling ball across the seesaw, you would be able to know the arc length that rolled across the ground, but beneath it, the actual surface you're rolling on has changed angle, right? Assumingly it had enough weight to change let's just say it's a 800-pound bowling ball or something. It's a very strong, very strong seesaw. It would have enough weight to bend or to get one side to change angle, and that's what it's relating. It's relating the angle change of the ground and the arc length of the distance you're putting onto the ground, essentially. Does that make sense? I feel like this is the Jackson show. He's just sitting here answering all the questions for everybody. I think everybody's in the other room watching their soap opera or something. Yeah, Sean likes General Hospital. So, depending on what year he was born in, though, he might not know what General Hospital is. But anyway, I'm showing my age again. All right. One life to live. Anyway, so what I planned on doing, I planned on doing this question. So obviously that took a lot longer than what I wanted it to, because this is very important. You'll be dealing with rolling contact for quite a while, so it's very important that everyone knows exactly how it functions. We were planning on doing this right here. Nope, that's not what we were planning. This one right here. We were planning on this. So what I'm going to do is I am going to probably tomorrow, I'm going to post a video online of me solving this, and you guys can watch it and follow along. Essentially, the only difference between this one and the other ones, how about this? We'll just talk about it really fast. It'll probably be another 10 minutes or so. So we're not going to solve it, but we're going to talk about it really quickly. So this right here, you guys might be wondering, you're like, man, this has got a lot going on, right? This question has a lot going on. So if we were to follow our protocol is vector loop, right? I think everybody remembers how we do these. Vector loop. 2 was, why did I do that? 2 was knowns and unknowns. 3 is so it's vector equation. And scalar equations. And so real quick, the vector loop is something we all know, right? You create the vector loop, it has to come back in on itself to create a full loop. Knowns and unknowns is what is changing and what is not, or things that we know. And vector equation is the very simple, like, R2 plus R3 plus whatever, right? And then the scalar equations are the x and y component of that previous one, which is like, R2 cosine theta 2 plus R3 cosine theta 3, right? So, real quick, if we were going to solve something like this, you guys might be wondering, how can we solve this, right? Because so far we've only ever seen, questions that have one vector loop, right? And you guys would go, well, how would you do this in one vector loop, right? You'd probably go something like this. And remember, sliders have to go like up, right? Down, up, and all the way back, right? You would probably do something like that. Maybe. Shake your head yes, that's what you would have done exactly. Just play along, guys. Come on. So, if you did something like that, I'm not saying you couldn't do it, but it might not be worth your time to do it. And what I mean by that is you might find that there are a lot of things that are unknowns, and you might have to get a bunch of new equations to solve for, because as you can see on here, there's no rolling contact equation, so you're not going to get bailed out by that. You're not going to get bailed out having one extra equation now, so you'd have to come up with ones yourself. You'd have to come up with all those extra equations yourself to solve this in one vector loop. Or, there's another way. But wait, there's more. You could do it in two. And so, let's do that really quickly. So if you did this in two, I think everyone in here would probably remember these are just revolute joints. So what you would do is you just go straight across the revolute joint. We'll call this R2. Right? And then from here, I think everyone would probably go to 3, right? And then, once again, I think everyone in here would probably go all the way down here to the other one, which we're going to call this, we'll call this R4. And then mostly everybody would probably go all the way back up for R5. Let's call it R5. And then, once again, remember, R1 is usually held to connect the grounds. So let's call that R1. R1. If you did this loop, let's go through it really quickly. So this first loop, we're going to call this loop Loop 1. Loop 1, what are the knowns and unknowns of this? So let's go with knowns. Like I said, knowns is pretty useful because everything else is basically unknown. So would you guys consider R2 to be known? We need yes or no's here. I'm going to ask you yes or no questions. So you would say yes. So R2, known. Theta 2. Would you guys consider theta 2 to be known? You would say unknown. Why? Rosendo has another answer here. So remember, guys, remember what I told you theta 2 always is. Theta 2 is always the input link in this class, which means that it is unknown as a quantity, but we are the ones controlling it, right? So it is something that you should always put into here. Theta 2. So, known. What about R3? We know R3. Correct. What about theta 3? Look at how this thing moves and determine it. Do you think we will know theta 3 at all times? The answer is definitely no, we will not. So let's go through, and I will put that as the unknown category. Theta 3 is our first unknown. And the reason is because, depending on where you put your coordinate system, but I have a feeling that you guys are going to put your coordinate system right here to eliminate R1, right? Its angle. As this thing moves, so essentially R3 is almost directly on the coordinate system as it stands. As this thing moves, like let's say this slides up here, or we pull this back, which is what it would be, we pulled this back, would R3 be on the exact same line as it is now? The answer to that is pretty clearly no. So theta 3 is our first unknown. I agree with you. Let's go with R4. R4, is that known? Let me get rid of this. Yes, correct. R4 is known. It is known, as the Dothraki would say. Anyone who likes Game of Thrones. Anyway, so R4, known. Theta 4, is Theta 4 known? At all times. Correct, Junlin, it is not. So Theta 4 is also an unknown. And that is simply because Theta 4, we're going to call it this right here, this angle. It's, we'll just say this. It's basically this. As this thing swings upward, Theta 4 will not be on this exact same line again. It will be somewhere else. So Theta 4 is unknown. I agree with you. So let's try the next one. What about R5? R5, I agree. What about Theta 5? Let me make sure this one actually has a Theta 5 in it. It might not. Oh yeah, it does. I was right. Okay. You'll know Theta 5 at all times? Are you sure? So remember, Theta 5 is this vector right here. As we pull it this way, will this vector be on that exact same line again? I think Junlin is correct here. Theta 5 falls into the unknown category. And so I know we're doing this really quickly, but generally speaking, you would draw out each of these vector, or each of the coordinate systems, and you could show as this thing moves, although you can't really show it, obviously, because it's a picture, but if you move it in your head, right, if you pulled this corner this way, this one would have to come with it, right, and therefore R5 is now over here somewhere, right, so it is no longer at that exact same angle, you see? Now, the last one, what about R1? Is R1 known? At all times? The answer is yes, because we have a grounded right here and a grounded over here. Those grounds are not moving, so R1 is known. What about Theta 1? Theta 1 is also known, and that is because we drew our coordinate system to go right along R1. Therefore, we have eliminated Theta 1 as an unknown, right? We've eliminated it. We made it, or we did. So the thing is that Theta 1 was never changing, even if you put your coordinate system in a different place, Theta 1 would never change. But the reason why you do it is to make your equation easier. So like, for example, the cosine and sine portion go to 1 and 0. That's why you do it. It's not really to eliminate them as unknown per se, because they're never changing, because obviously here to here is never changing angle. But it's to make your equation simpler. It's a very crafty way of making your equation easier in the end. So I guess I should rephrase. So for this vector loop, we now have, how many equations did we get out of this vector loop? Only 2. So we had 2 equations, and we have 3 unknowns. So as we are currently standing, this cannot be solved, right? It can't be done because we don't have the proper number of equations to do it. But don't fret. So let's hold on to that for now. We have to now do another vector loop, right? Because there's one big part of this that we didn't actually pick up. And I'm going to draw this one in red so we can see the difference. So we didn't pick up this slider at all. And so, like I said, the point of a vector loop is to properly show the mechanics, the movement of one of this mechanism, right? And if we don't pick this up, well, then we didn't do that, right? We've neglected to do that. So, real quick, if I were you, I would go straight to it right now. So we could just go from here to here, right? And you can call this whatever you want. They call it R21 in the book, because once you use up a certain number of these, they kind of flip back and go to 2-1 and 2-2 and 2-3, right? You know, stuff like that. But we're going to call this one R21. Now, how do we do sliders? Anybody remember how we do sliders? Along the channel, agreed. So, along the channel, like that. And then let's go. I'm trying to draw this better. It's hard to do though. Yeah, I'm trying to make it to where it's showing. It's showing in some that it's not on top of the other line. I'll try that again, actually. God, that sucks. Okay, let's try that. That seemed a little better. Okay, so we called this R21. This one we can call. So remember, we're on link 4, so we can call this one whatever you want in the book, just so you guys know. You guys can find this one in the lectures at least. They call this one R41, right? R41. And then they have this little connection of 90 degrees. And then what do they call this other one? Oh, they call it R42. Okay, so I'm going to draw a line down to here. R42. It was getting a little cramped up there. So R42. And now, where would we go now? We don't want, remember this, so the whole point of the vector loops is to minimize unknowns, minimize equations, minimize unknowns. So what could we do now to not add any more unknowns or any more equations, essentially, right? Or any more unknowns? What could we do? Remember, we have to loop back to where we started, so how would we do it? It's often the easiest answer. Let's put it that way. Yes, so Junlin is correct. So essentially, we are going to follow that exact same line as up here and go back the same way down here. But I'll twist it so you guys can see there's another line under it. So, what we did there was that we added another set of equations, so we got 2 more equations out of that vector loop. So now we have 4 total. But now you guys are probably going, well, we added some unknowns. We sure did. I agree with you. We definitely added some unknowns. But this part right here at the end made it to where we did not add any more unknowns from the end of it, right? We only added unknowns from this part. If you would have tried to do something different, you might have added more unknowns. You probably could have done this. You probably could have gone the reverse. You could have gone back this way, and this way, and it wouldn't have changed anything. But this was the easiest way, right? Basically, if you get to the end of your second loop and you have a choice between following a path of things you've already created versus creating a new path, you should follow the path of things you've already created, because you don't want to add anything new to it, because once again, your whole point of this is to minimize how many you have to find. Alright, so real quickly, we're going to just do the unknowns for this one as well. Loop. Oh man. Can you imagine you spelled that one wrong? What did I do with Epic Pen? Ah, here it is. Lop. So, let's try this one. Loop 2. So loop 2, so let's do knowns and unknowns. So R21, is R21 ever going to get bigger? Think about this one. Look at the mechanism, not the vector length. I'm going to give you that one. Look at the vector, or look at the mechanism. Do not look at the vector. Or do not look at the vector length. Rosendo says unknown. And Jackson is coming at us with something else. Hopefully. He's not. Alright, he stopped. He gave up. So real quick, R21 will never get any longer. And there's a reason why it won't, is because, remember guys, R21 is essentially this revolute to this pin. And as this thing slides up here, this distance doesn't change because it's attached to the same point, right? Essentially, this has to move with it. It's all on the same link, right? So it's basically like saying this distance will never change. No matter how this thing moves. It will not. So that's why you have to be careful about, once again, look at the mechanism rather than what the vector looks like. Because you guys probably went, oh, well, yeah, if this thing slides up this way, then this had to get longer, right? Well, if it does slide up this way, this whole part has to move back towards this one, or else it won't work. So you guys have to be careful about how you look at these things. So R21 is definitely known. What about theta 21? Now this one, you guys should definitely have. Will this angle be the exact same if it slides up to here? Which would be, that is definitely, yes, it will not be. So theta 21 is right here in an unknown pile. What about R41? Will R41 stay the same? Which R41 is defined by this touching this pin to this point. Will it be the same? It will not be. You are correct. So R41 will not be. What about theta 41? So real quick, theta 41. So right here, as it currently sits, it's pretty close to right on the line here, right? Right on our coordinate system, right? It's pretty close. So take this coordinate system right here, apply it to this line, and now let's move the mechanism. Let's have this thing swing way out this way, right? Will R41 be on that exact same line? Or that exact same angle. Not on the same line, on the same angle. That's what I meant. Not line. Because it will be on the same line. We've drawn it that way. You said it'll be on the exact same angle. So if we swing this out this way. So remember, this follows this channel, right? Jackson, so this R41 follows this channel. If we swing this whole mechanism, if we take this R5, or this link 5, and we swing it way out here, right, and we pull it as far away as possible, this slot that it follows is no longer at this exact same spot, right? It is now kind of changed in its direction, you would say, right? It's now moving slightly different than it was before. It's still following the slot, but the slot, yeah, it can swing because it's revoluted up here. Yeah, so you got it. So we would put that one down here as another variable, which would be or what did I say, theta 41? Yeah, theta 41. Sorry, lost that one for a second. What about R42? which is right here. So that distance will never change. I'm going to try and get us out of here because we're way over. So R42 will never change. And the reason why it will not is because this distance, it's essentially, so as this thing swings, the angle of this vector has changed, but the distance from here to here is just some distance we've drawn. It's from this point to this point on the link. And so that distance is never going to change. We have set it up to where it won't, right? So R42. What about theta 42? Theta 42. Now remember what theta 42 is. So essentially, this vector 42 is just a distance here to a distance on this line, right? To a distance on this line. Theta 42 is the angle of which this line is moving, right? Or is it's pointed. So as this thing changes, as this 41 changes, 42 also has to change, because if it doesn't, it won't meet at that same point. It will get longer. So theta 42 does have to change. This one does. And now you guys are probably wondering, well, wait a minute. We now have all these unknowns. We have 7. How the hell are we going to solve this, right? That's probably what you're wondering. You're like, well, wait a minute. How are we going to do this? And by the way, that's the end of it, because we go right back on the same loop. You guys are probably confused how we're going to do this. So real quick, we have 4 equations total, right? So far, we have 4. We have 4 because we have theta, we have both of the scalar equations, right? So we have 4 total so far, from 2 from here and 2 from here. So that means we need 3 extra equations. 3 extra equations. So can anybody tell me where you might see 1? Remember what I told you to look out for. We're just going to identify them. We're not really going to spend time on them. I told you to look for sharp corners, right? Right angle, correct. So there's 1 right here. And so if you were to write this, you would write, so I'm going to write add equations. So these are additional equations, right? Maybe not. We'll try that. So I'm going to write the additional equations down here. So if you were to write this, you would write theta. Why did we switch to the highlighter? You would write theta 41 plus pi over 2 is equal to theta, not theta 4, theta 42. So if you look at this, R41 is here. It's going this way. If you add pi over 2, you would now get on this line, right? You guys can agree. I think that's how they wrote it. Yeah, that's how they wrote it. Okay. But you could do the reverse as well. You could do theta 42 minus pi over 2, right? But I wrote it that way. So that's the first equation, right? So this is equation 1. Equation 2. So this is where these get a little bit more, involved. And so this one's going to be interesting. So actually, this one's going to be really hard for us to explain probably in the time. But essentially, what they did was they related theta 21, which is this angle, right? So theta 21 is very clearly this one right here, right? Theta 21. Theta 2 is this one right here, right? So it's from this, or no, it's not that. That's my bad. Theta 2 is from here to here, right? And what they did was essentially they wrote alpha 2, which is, remember what I told you is that you can relate things to total lengths, right? Or total angles instead of just sharp angles. That's what the next 2 do. So essentially what they do is they go theta 2 minus alpha 2, I think is how they do it. And remember, alpha 2 is just some variable name, right? Is equal to theta 2, 1. And alpha 2 is defined as, I think it's this total one. Yeah, it's this right here. So it's alpha 2. And so what that means is essentially it gave you a way of relating the two together, right? Essentially, theta 2 and theta 21 are the same angle if you use this. If they're not this, okay, so they're not the same angle. They are basically this number apart. And so if through your equation solver you were able to find one of these, right? It would plug numbers in, I guess, to find, or if you could find, basically let's put it this way, if you could find one of them, with this equation you might be able to find the other. And basically what I'm saying is you're trying to relate one to the other in some way, right? And now the third one does the exact same thing, but it does it right here. It does it between 4, 1 and 5, I think. Oh no, it does it between 4, 2 and 4. Sorry, that's my fault. So let me get rid of this stuff. So it does it between here. So theta 4, so what it says is the difference between theta 4 and theta 4, 2, which right now, guys, you can see that they are almost the same, right? Like theta 4, 2 is here, theta 4 is here. Essentially, it writes it as theta 4 minus alpha 4, which alpha 4 is just the difference. It's just the whole way around rather than just the middle part in between. Here, I'll just write it. It'll make a little more sense if I do that. So it's, I think, theta 4 minus alpha 4 is equal to theta 4, 2. And if you draw the coordinate system, I said this will make things a lot, I know it'll make things a lot easier, but the coordinate system is like here, right? How we drew it. So alpha 4, or theta 4 is this, right? It is from here to here, right? Theta 4, 2 is from here to here, if I recall. Yeah. And so what it's saying is that these two angles with the subtraction, or theta 4 with the addition, oh, I should have wrote that differently. It should be the addition of, not the opposite. It should be the other way. So it should be theta 4, which is here, plus alpha 4. So alpha 4 is like the difference between them, is equal to theta 4, 1. So it's the exact same way as the other one. Now, I'm just going to tell you guys, this right here doesn't show up very much. Like, you don't have to do this alpha 4 and alpha 2 stuff very often. But, well, actually, I think this is like one of the only questions I've ever seen it on. So I'm just showing you the worst case scenario. The worst case scenario is this, right? The worst case scenario is this. Most of them are just simply things like this, right angles or difference of angles like that. They're not this they're not very much of this alpha stuff. So real quick, I'm going to get us out of here. It's been a long class, been the longest one ever. I'm going to take attendance, and then you guys are free to go. So let me get this off the screen. And stop recording.